Now, if you remember at the beginning of this chapter, I said in one of the videos that aromatic refers to stable. Okay, so aromatic doesn't necessarily mean fragrant. It means a remarkably stable compound. And if you go back to the chapter on alkenes, which would be chapter 8, we said if you take an alkene like cyclohexene, that's this compound here, treat it with bromine, it adds, we make the bromonium ion, then a bromide comes in and attacks from the opposite face of the molecule, and you end up with this trans 1,2-dibromocyclohexane. And so the conclusion is alkenes can undergo addition reactions no problem. That's the whole topic of chapter 8 in Organic Chemistry 1. However, if you take benzene and treat it with bromine, nothing happens. You get no reaction, and you might think, well, come on, I've got a double bond here, I've got a double bond here, and I've got a double bond here. Shouldn't I get a reaction? Well, like I said, there's no reaction, and the reason why is because aromatic compounds are stable. Now, let's talk a little bit more about the stability of benzene. Now, take a look at this diagram very carefully. It's a diagram that shows the heats of hydrogenation of cyclohexene, 1,3-cyclohexadiene, and a theoretical compound called 1,3,5-cyclohexatriene, and then also benzene. So a few different compounds on here. So just take a look at this. If we take cyclohexene, okay, and we do a hydrogenation, right, using hydrogen, palladium, platinum, or nickel, okay, and we hydrogenate it down to cyclohexane, and they put it in a chair form here. They could have just as easily written this, okay, nothing wrong with either one, okay. Well, what we do is we release about 120 kilojoules of energy, okay? So that's for one double bond. So you might think, okay, well, if I have two double bonds, then I'm going to release 240 kilojoules of energy for every mole that I burn, okay? Not that I burn, that I hydrogenate. But you can see here that we release a little bit less than 240. It's actually 232 kilojoules per mole of energy that is released for our 1,3-cyclohexadiene, that's this compound here. And the reason why we don't release exactly 240 kilojoules is because of the stabilization that comes with conjugation. And if you don't remember what conjugation is just when we go double, single, okay? So the conjugation adds some stability. But then the compound up here on the top in red, okay, this is actually a theoretical compound. I know it looks just like benzene, I get that. But let's imagine there was a compound called 1,3,5 okay? So if you had this theoretical compound, okay, and you hydrogenated it, it should release a little less than 360 kilojoules per mole, right? A little less than 360 because of the stabilization that comes with conjugation. But in fact, what happens if we try to hydrogenate benzene, which is shown here, and benzene is an actual compound, it actually releases only 208 kilojoules per mole of energy. And so what that tells you is that benzene is 150 kilojoules per mole more stable than you think it might be, than you might expect it to be, okay? Now, why is that? Why is it that benzene, when it does get hydrogenated, why does it release such a small amount of energy? Again, it's because it's stable. Well, where does this stabilization come from exactly? And in order for us to explain the stability of benzene in real detail, we need to invoke molecular orbital or MO theory. Now remember that a pi bond results when we have two atomic p orbitals overlapping side by side or side to side to form two new orbitals called molecular orbitals. Remember that one is going to be a bonding molecular orbital, which will be lower in energy, and then we have an anti-bonding molecular orbital that's going to be higher in energy. And so if we form a pi bond, both pi electrons would end up in the bonding molecular orbital and therefore achieve a lower energy state. Now, if we look at the molecular orbital theory that describes the nature of benzene, which is comprised of 6 overlapping p orbitals. So you see them here. We have 1, 2, 3, 4, 5, 6. I know that picture's cut off a little bit, but what they're trying to show you here is those are the p orbitals in benzene. So I'll just draw it out like this. Remember, each carbon is sp2 hybridized, right? Each one of these guys is sp2 hybridized, and therefore they all have a p orbital on them. So the precise shape and energy level of each molecular orbital are determined by sophisticated mathematics that's beyond the scope of this class. But for now, let's just focus on the important concepts that are illustrated by the energy diagram that we see down here at the bottom of the slide, right here. So we have 6 atomic orbitals, so 6 p orbitals, right? 1, 2, 3, 4, 5, 6. So we combine those 6 atomic orbitals and we end up with 6 molecular orbitals. Look, 1, 2, 3, 4, 5, 6, okay? Don't worry, you won't be asked to draw any of these, but you should understand that the number of atomic orbitals, so if I write down here, the number of atomic orbitals is going to be equal to the number of molecular orbitals. So we took 6 atomic orbitals, we're going to end up with 6 molecular orbitals. Now, 3 of the molecular orbitals are below this dashed line that are shown here. And the ones that are below the dashed line are called bonding molecular orbitals. The ones that are above the dashed line are called anti-bonding molecular orbitals. Now, since each molecular orbital can contain 2 electrons, and we have a total of 6 pi electrons, that means that every electron is going to end up in a bonding molecular orbital. And you can see it shown here. I'll zoom in a little bit, but you can see we have 1, 2, 3, 4, 5, 6, right? All of our pi electrons end up in bonding molecular orbitals. And by occupying the bonding molecular orbitals, all 6 electrons achieve a lower energy state than they would have been in their p orbitals and are delocalized. And since the bonding molecular orbitals are filled with paired electrons while the antibonding molecular orbitals are empty, benzene is said to have a closed shell electron configuration, and this is the source of stabilization energy associated with benzene. So I'll repeat that, okay? Since all of the electrons are in the bonding molecular orbitals, we say that benzene has a closed shell electron configuration, and this is what contributes to the stabilization of benzene. Now, based on what we've seen so far, you might think, okay, well, anytime I have conjugation in a ring, I'm going to have an aromatic compound. But it turns out that the 2 compounds on the top here, cyclobutadiene and cyclooctatetraene, neither of them are aromatic. If you take cyclooctatetraene, this compound right here, and treat it with bromine, hey, it does an addition reaction like nothing, okay? And if you take cyclobutadiene, which is a very difficult compound to isolate, if you do isolate it, it just does a Diels-Alder reaction, so that's what's happening here. This is a Diels-Alder reaction. And then it rearranges after it forms this tricyclic compound, and it just gives you some cyclooctatetraene. And so that tells us that it's not just conjugation in a ring that makes an aromatic compound. And so in order for an aromatic compound to exist, 2 criteria have to be met. First of all, you have to have a fully conjugated ring with overlapping p orbitals, okay? And you see that here, and you see that here, and those compounds are not aromatic, so there must be more to it. And in benzene, forgive my messy drawing here, we also see, right, we see the conjugation here in the ring. So the second thing is this, is that it has to meet Huckel's rule, or it has to have an odd number of electron pairs, or 4n plus 2 total pi electrons, or n is a whole number, 0, 1, 2, 3, 4, 5, 6, 7, 8, etc., etc. And so these 2 compounds that we see here, the cyclobutadiene and the cyclooctatetraene, they do not meet Huckel's rule. Now let's go over this very carefully. Both of them have a conjugated ring with overlapping p orbitals, right? If we look at it the way it's shown here, every single carbon in both of these compounds is sp2 hybridized, and so each one should have a p orbital on it. Okay, I'm not going to bore you by drawing every single one of them, okay? But the first number here, number 1, looks like it's met. But remember, it says here an odd number of electron pairs. What is a pair? A pair is 2 of something, so 2 electrons. So watch very carefully. In this pi bond, there are 2 electrons. In this pi bond, there are 2 electrons. So that's 2 pairs. Is 2 an odd number? No, 2 is not an odd number, and so therefore this is not an aromatic compound, okay? Let's take a look at the cyclooctatetraene. Here we have a pair, here we have a pair, here we have a pair, and here we have a pair. That's 4 pair. Is 4 an odd number? The answer is no. 4 is an even number. And so neither of these meet Huckel's rule. Now, if you're like, what's the 4n plus 2 thing? 4n plus 2 is just a formula where you substitute 0 in for n. Let's do the math. If you have 4 times 0 plus 2, what do you get? 2. If you have 4 times 1 plus 2, what do you get? 6. If you have 4 times 2 plus 2, what do you get? 10. So on and so forth, okay? So if you take a look here, you see that we have 1, 2, 3, 4 total pi electrons. That does not satisfy 4n plus 2. Here we have 1, 2, 3, 4, 5, 6, 7, 8. That does not satisfy 4n plus 2. Again, I'll repeat. Look, to satisfy 4n plus 2, if n is equal to 0, then the total number of electrons, 4 times 0 is 0 plus 2 gives you 2. So I'll just put here, number, we'll put here 2, okay? If n is equal to 1, what's 1 times 4 is 4 plus 2 gives you 6, okay? If n is equal to 2, 2 times 4 is 8 plus 2 gives you 10. If n is equal to 3, 3 times 4 is 12 plus 2 gives you 14. So you see here we have 4 and here we have 8. Those numbers are not shown here. The numbers are 2, 6, 10, and 14. We call those Huckel numbers. What do you notice about these numbers? If you divide all of them by 2, so if you take them and you divide by 2, so we'll just put here 2, divide by 2, you get 1, 3, 5, and 7, so on and so forth. So you end up with an odd number, okay? So this is where Huckel's rule comes from. So again, it's an odd number of electron pairs, or it has to satisfy 4n plus 2. But what I'm demonstrating for you right here is how when you satisfy 4n plus 2, when you plug in 0, 1, 2, 3, etc., the number of electrons that you get when you divide it by 2 to give you the number of pairs, it always gives you an odd number, okay? You might have to listen to that or read it a couple of times, but it is logical. And so what's the requirement for an aromatic compound? It has to be cyclic. It also has to be planar, and we're going to get to that in a second. It can't have any sp3 hybridized carbons in a ring. It's got to have conjugation of pi bonds. This is supposed to be a pi here. It has to obey Huckel's rule, 4n plus 2 pi electrons, where n is a whole number, 0, 1, 2, 3, 4, and that is what makes an aromatic compound. So if I just took this off of Google, so if this is helpful for you, then I'm glad. Now let's use molecular orbital theory to explain the source of Huckel's rule for planar conjugated ring systems. We already looked at the molecular orbitals of benzene to explain its stability. Now let's turn our attention to the molecular orbitals of cyclobutadiene and cyclooctatetraene and see how molecular orbital theory can explain the instability of these compounds. Let's start with the square cyclobutadiene that's shown here, which is a system constructed from the overlap of 4 atomic p orbitals. You see them here, 1, 2, 3, 4, right? Every single one of the carbons in this molecule is sp2 hybridized, okay? And so according to molecular orbital theory, these 4 atomic orbitals, right? All 4 of them are going to be replaced with 4 molecular orbitals with the relative energy levels that we show here. We have 1 bonding molecular orbital, we have 1 anti-bonding molecular orbital, and then we have 2 that are right in the middle, okay? And those are our non-bonding molecular orbitals. But we have a total of 4 pi electrons, and when we start putting them into the molecular orbitals, you notice that 2 of them are in a bonding molecular orbital, but 2 of them are in non-bonding molecular orbitals. And so therefore, you notice that there's a difference in the electron configuration for benzene and this molecule. In the case of benzene, all of the pi electrons are paired in bonding molecular orbitals, giving that closed shell electron configuration. In contrast with this molecule, cyclobutadiene, it lacks that closed shell electron configuration, and that explains its instability. Now, due to this unusual instability, the compound is said to be anti-aromatic. Okay, cyclobutadiene can alleviate some of its instability by adopting a rectangular shape in which the compound functions as 2 isolated pi bonds. And so cyclobutadiene lacks the closed shell electron configuration, and it's unstable, and so we say it's anti-aromatic. Now let's take a look at the cyclooctatetraene. And we see something similar with the cyclooctatetraene. We have a total of 1, 2, 3, 4, 5, 6, 7, 8 sp2 hybridized carbons. So that means that each one has a p orbital, 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 atomic orbitals. 8 atomic orbitals. So that means we're going to have 8 molecular orbitals, and you see them here. We see that 3 of them are down here, are bonding molecular orbitals. 3 are above the middle line. Those are anti-bonding molecular orbitals. And 2 are right in the middle in these non-bonding molecular orbitals. And thus we can conclude, since all of the pi-electrons are not in bonding molecular orbitals, we have 2 of them that are in non-bonding molecular orbitals, that it is not an aromatic compound, and so it suggests that this is an anti-aromatic compound. However, there are actually very few anti-aromatic compounds. Anti-aromatic compounds are highly unstable, and so what happens is oftentimes molecules will adopt a configuration or a shape in order to avoid being anti-aromatic. So let me show you what cyclooctatetraene does to avoid being anti-aromatic. And what it does is that it adopts this tub shape here. So you can see this is the tub shape, okay, here. And the reason it does that is because when it adopts this tub shape, you have no overlap between these p orbitals here. So you don't have a continuously overlapping system of p orbitals. So it breaks that overlap. And so it makes the compound not anti-aromatic and not aromatic. It's neither, okay? It's in between. It's actually what we call a non-aromatic compound. And so to summarize, and you should memorize this, okay? Cyclobutadiene is an anti-aromatic compound. I'll put AA like this. And cyclooctatetraene, this guy here, okay? Cyclooctatetraene is non-aromatic. So I'll use Na for non-aromatic and AA for anti-aromatic. And again, you have to memorize these. The reason why cyclooctatetraene is non-aromatic is because it adopts this tub shape, which prevents the continuously overlapping system of p orbitals from happening. Now, if you're looking at these molecular orbital diagrams and saying, where did you come up with these? How did you figure out what these molecular orbital diagrams are? Am I going to be expected to do this? Well, the answer is it's not that difficult if you use something called a Frost circle, and you have to know how to draw a Frost circle. And predicting the shapes and energies of molecular orbitals can be simplified greatly by using Frost circles. So here's what we do. It's a 5-step process. The first thing we do is we draw a circle, okay? Then whatever the shape of our cyclic compound is, let's say in this case they chose a 1, 2, 3, 4, 5, a 7-membered ring, okay? You inscribe your polygon inside your circle, making sure that one of the connecting points is touching the bottom of the circle. So here you see they have a 7-membered ring, so they just made sure there's a point touching at the bottom like this, okay? Then you draw a horizontal line everywhere that a point intersects the circle. And so you see here we have a total of 7 lines. Then you draw a dotted line right through the middle, okay? Everything above is an anti-bonding molecular orbital. Everything below is a bonding molecular orbital. And if you're saying, well, what if I had something like this? Like what if I had the cyclobutadiene, which is a square, and if I drew a square inside my polygon, oh, forgive me, I'm not very good at this. But anyhow, what would I have then? Well, in that case, you'd have 1 bonding molecular orbital, 1 anti-bonding, and the ones that are right in the middle, those would be non-bonding. Okay, so don't stress, okay? If you have some in the middle, exactly in the middle, those would be non-bonding, okay? And these were developed by Arthur Frost, a pretty magnificent way of coming up with a molecular orbital diagram. And so the Frost circles help us to rationalize Huckel's rule, the 4n plus 2 rule. Notice that as you go from a 4-membered ring to a 5-membered ring, 6, 7, 8, 9, and 10, if you look at the number of bonding molecular orbitals, look, when we have a 4-membered ring, we have 1 bonding molecular orbital. So if we have 1 bonding molecular orbital, 1 is an odd number and it can hold 2 electrons. Well, that would be 4n plus 2, or n is equal to 0. 4 times 0 is 0, plus 2 gives you 2. Then if we have 3 bonding molecular orbitals, which we see when we have a 5, 6, 7, or 8-membered ring, well, 3 times 2, 1, 2, 3, 4, 5, 6. That would give you 6 pi electrons. Well, that would be 4n plus 2 when n is equal to 1. 1 times 4 is 4, plus 2 gives you 6. So there you go. And then if you go to n is equal to 2, so if we change this to n is equal to 2, 2 times 4 is 8, plus 2 gives you 10. So take a look. When we have 5 bonding molecular orbitals, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And there you go. So the frost circle helps us, or helps give us a rationale for Huckel's rule. So we notice that the number of bonding orbitals is always an odd number, 1, 3, 5, 7, so on and so forth. And aromatic compounds will always have an odd number of electron pairs, 1, 3, and 5 in the examples we see on this page.